Swayam Prabha. Digital India. Educated India.
What is the, if a lay person were to ask you, as a student of science, what is the most basic quantity in this universe, the currency of the universe, so to speak? What would you think? What would you say? Energy. It's definitely energy. So everything has to do with the transformation of energy from one form to another, the exchange of energy from one source to another, and so on and so forth. Now, the moment you understand that, you have to also appreciate that different parts of physics, taking physics specifically, have different energy scales attached to them. There are different energy scales attached to nuclear physics, for instance, as compared to atomic physics, or to condensed matter or solid state physics as compared to nuclear physics, for instance. So let me ask you a few energy scales. What would be a typical energy scale if you were studying atomic physics? Would it be hundreds of electron volts, thousands of them, millions of them, or 10 to the minus 3 electron volts? What would be the typical energy scale if somebody were to ask you this? Well, first of all, energy in physics, in nuclear, atomic, and subatomic physics, is measured in electron volts rather than in joules. So we need to know the conversion factor right away. What is 1 electron volt in terms of joules? Yeah, so the 1.8 is not very relevant. It's whatever number it is of order 1. But what's the power of 10? How many joules is 1 electron volt? That you must have cold, absolutely. First of all, let's understand how much a joule is. Just to get an idea of what a joule is, if I took a weight 1 kilogram in weight, lifted it up by a meter, about 3 feet or 4 feet or whatever, and dropped it, what would be the kinetic energy at the point of impact? What's the potential energy if I lift a 1 kilo weight by 1 meter against this gravity? 10 point? 9.8 is roughly 10. Roughly 10. So it's of the order of 10 joules. The potential energy, or conversely, if I drop it, the kinetic energy at the time of impact is of the order of 10 joules if I take a 1 kilo weight and drop it from a height of 1 meter. It's about 10 joules. So that gives you a reference point of what this size of this unit is, called the joule. Okay. Now, how many joules is an electron volt? Yeah, so as physicists, as scientists, it's not important for you, except in exams, of course, to remember this 1 point, whatever it is. I'll constantly forget about this 1 point, whatever it is, 2 point or 3 point, it doesn't matter. But the power of 10 is very important, very, very important. It's no use if you know Planck's constant, 6 point, whatever it is, 6 point. It's true. Yeah, if you forget the 10 power minus 34 or you write it as 10 power plus 34, you're making a small error of 68 orders of magnitude. That's important. Leave aside, leave the numerical factor of order 1, that's not relevant at all. Okay. So 1 electron volt is 10 to the minus 19 joules. It's really tiny, very, very tiny in these macroscopic units like joules. But since in atomic physics, the electron volt is in fact the scale of energy at 10 electron volts or so, it's a good idea to talk in terms of electron volts in atomic energy instead of keeping this 10 to the minus 19 all the time. It's not worth it. Okay. How would you determine the scale in atomic energy, in atomic physics? What would be a scale of energy? What's the simplest atom you can think of? The hydrogen atom. So does it have an associated energy scale with it? There are energy levels, many levels, but what's an energy scale? Somebody would ask you, what's a typical energy scale on which this whole thing operates? What would you say? Pardon me? The energy of an electron depends on the level it's in the ground state or the normal state. So we leave it alone, it goes to the ground state. And in that ground state, You don't measure energy absolutely in non-relativistic physics. Because if I say the potential energy of this object is mgh, h being the height above ground, that means I've set the zero of energy to be the ground level. I need not have done that. I could have set the zero of energy to be at the bottom of a pit 10 feet, 10 meters deep. So what is relevant in non-relativistic physics, where you don't worry about the rest energy of a particle, is the differences in energy always. It's only energy differences that have some meaning. Otherwise, the absolute value of energy does not have any meaning in non-relativistic physics, really. Relative to the ground level being zero energy, potential energy, the energy of this object is mgh, height above ground, h being the height above ground. Similarly, what would you say is an energy scale, characteristic energy scale for the hydrogen atom? What is this minus 13.6? Minus, what is this minus?
That energy supplied it's assumed to be free electron without any potential.
Yeah, he's got a good point. He says you assume the free electron, we will have zero energy, but make that more precise for me. Would you agree that if I said, take this hydrogen atom in its ground state, one electron in its ground state, the amount of energy I have to supply to this hydrogen atom in order to kick that electron out of its orbit into separating into a proton and an electron very far apart with zero energy, that would be the energy scale. Would you agree with that? What's that called? What's the energy required to kick out an electron called? It's called the ionization energy. So you already know it. You see, I just have to press the right buttons. So the ionization of a hydrogen atom in its ground state sets you an energy scale in atomic physics. Okay. The rest of it is all fluff over it, and it's dressing over this. Okay. If you had more than one electron, it would take a little more energy, etc., etc. All kinds of complications can happen. But the basic energy scale is of the order of 10 electron volts. 13.6, 10, they're the same thing, same order of magnitude. Okay. What would be the ionization energy of helium? What's the first question you should ask me if when I say what's the ionization energy of helium? We'll assume it to be in the ground state, but what would you say is the energy scale? Helium has how many electrons? 2. So when I say ionization energy, I have to tell you, is it the energy required to remove one electron or 2 electrons or both or the second electron or what? Okay. Which would be more expensive? To remove an electron from the helium atom or to remove the second electron from the helium atom? What do you think? Why? Why? Okay. In Bohr's theory, which gives you a first approximation. Wait, let's have. No, the point is two effects come into play. Helium is a complicated object. There are all sorts of quantum correlations between the two electrons. This took a long time to solve after the advent of quantum mechanics, but now we have a fairly complete answer to this. The first electron, very roughly speaking, when you want to remove one electron, it's already seeing a repulsion from the other electron. There is already a repulsion from the other electron. It's not a very significant effect at this stage. There's more important quantum correlations, but there is, very roughly speaking, some kind of repulsion. You remove that, then you got a charge 2 on the nucleus. So this will now, the second electron will be as if it's in a hydrogenic atom, but with a higher value of Z. Therefore, the binding energy will be larger in this case. It will take more energy to kick the second electron out. As you go further and further out, the Z factor in the nucleus goes on increasing, and then the inner shell electrons are very tightly bound, obviously. The outer shell ones are not so tightly bound. The ionization energy is less for those. Whatever it is, of the order of a few electron volts, 10 electron volts, very roughly in the ballpark figure for energy scale in atomic physics. What about nuclear physics? What happens when you come to nuclear physics? What is the simplest nucleus you can think of? Stable nucleus. Is there a hydrogen nucleus that's got more than one particle? Deuterium, right. We are talking about binding energies, and we are not talking about the binding energy of a single nucleon. That requires quark models and so on. But if you put two nucleons together, if you put two protons together, can you get a stable nucleus? Not with just two protons. How about two neutrons? Let's settle this gravitation business right away. Gravity is the weakest force of all. We don't fully understand it in the quantum field theoretic language, but it is 10 to the minus 38 times as weaker than the electromagnetic interaction. So it's completely negligible in particle physics. Gravity, for it to start playing a role, you have to have a huge amount of mass, like stellar masses or astronomical masses and so on. Otherwise, it's tiny. If I pick up a pin with a small bar magnet off this table, I have exerted a greater force than the entire Earth is exerting on it gravitationally. So this small magnet has outpulled the Earth completely. Okay? So gravity is extremely small. That's the reason why the detection of this gravitational wave was so tough, so incredibly tough. This enormous factor of 10 to the 38 that's sitting there makes sure that electromagnetic forces are that much stronger. Okay? Till you hit large masses. Then, of course, gravity becomes effective and becomes important. Of course, the Earth's mass is pretty high, so if I fall down a staircase, I do feel gravity very intensely. Not so much electromagnetism as gravity, but the level of elementary particles, the gravitational force is completely negligible. So what about two protons? Not possible. Coulomb repulsion. What about two neutrons? We don't know. We don't know without making further calculations. This is called a dineutron and it's unstable, it doesn't exist. Because you can show that the nuclear force between two neutrons is extremely weak, not stable enough to hold it together. How about a proton and a neutron? That's a deuterium nucleus. Yeah. Do you think it's stable or unstable? It is stable. Let's go back to the hydrogen atom. If I add an electron to the hydrogen atom, I get an ion which is negatively charged. Do you think that would be stable? There's only one charge in the nucleus. There's a single proton. So Z equal to 1. And the electron has an equal and opposite charge. But do you think I can put two electrons and get away with it? Can I ionize hydrogen? No, it doesn't immediately give it out. It exists. It can be experimentally verified. It can be experimentally implemented. You can, in fact, add a third electron. But that's extremely short-lived and extremely unstable. Not enough binding over there. Okay. Coming back to the nuclei, if you put a proton and a neutron together, there are nuclear forces between them and the net force is attractive. And this object is stable. That's the deuterium nucleus. What do you think is the order of the binding energy? That's a characteristic order of energy for nuclear physics. Have you seen this curve of binding energy? It's called the curve of binding energy for nuclei. Well, you're describing the shape of the potential in some sense. There's a short-range repulsion, a long-range attraction, and so on. But the nuclear force itself is much more complicated than that. It's not very easily approximated by a static potential. But the binding energy is calculable. It's also measurable. Turns out that the deuteron has a binding energy of 2.2 mega electron volts. So the characteristic energy scale in nuclear physics is mega electron volts. Not milli electron volts, mega electron volts, 10 to the 6th electron volts. And as you increase the number of nucleons, neutrons and protons, the nucleus becomes more and more stable and starts increasing in stability, till at the level of iron 56, you have the most stable nucleus. Everything above iron 56 is in principle decayable, can decay into it, although there are many nuclei there whose lifetimes are very, very large, essentially infinite and so on. Below it, you can cause fusion to go to more and more stable nuclei. But iron 56 is the ultimate, most stable nucleus. The number of the binding energy per nucleon in iron 56 is of the order of 7 mega electron volts. So this curve for the deuteron from 2, it increases gradually till it hits 7 per nucleon and then it goes down again as you go to heavier and heavier elements beyond iron. And certainly beyond uranium, things are unstable. They're artificial elements and they're unstable. Okay. So the characteristic energy scale in nuclear physics is of the order of 10 mega electron volts. Yeah.
Sir, you said that when you take a proton and a neutron and you put them together, the net force is attracted. Does that mean there are repulsive nuclear forces between
Yeah,
the
there
proton?
are repulsive effects also. It's not even approximatable by a single potential to start with. The force is not a central force, it's dependent on the spin, it's dependent on all kinds of effects and so on. And eventually you get a net force, which is effective potential between the electron, between the proton and the neutron, by which you can calculate its properties. But it is a very shallow bound state in the sense that it's just 2.2 mega electron volts. That's very low. It's not anywhere comparable to 8 or 7 or 8 or something like that. You need more nucleons for it. As you add more and more protons to the nucleus, it becomes more and more unstable because there's Coulomb repulsion between the protons themselves. So you have to compensate for it by adding neutrons. And it turns out that there is a band of stability. If you plot the neutron number against that proton number, there's a band of stability in which elements are stable. Outside it, they become radioactively unstable and they decay. This band of stability comprises many isotopes of elements. Roughly speaking, the number of neutrons is a little larger than the number of protons. If you make it too neutron rich, it again decays. If you make it too proton rich, it of course Coulomb repels and decays once again. It's not stable at all. In the case of hydrogen, you have hydrogen 2, which is deuterium, proton and a neutron. Can I add one more neutron to it? What do you get? Yeah. Is that stable or unstable? What do you think? Do you think that's stable or unstable? It's unstable. It decays, undergoes immediate decay in very short life. I don't remember the lifetime now, but it's unstable. Okay. It's the lightest radioactive nucleus, tritium. What about helium-4? How many protons, how many neutrons? That's extremely stable. That configuration is extremely stable. And the nucleus of helium-4 is what you are familiar with as an alpha particle. In the early days of radioactivity, they didn't know what the hell it was. They realized this charged object is very massive and it interacts in very funny ways, etc., with matter. They called it an alpha particle as opposed to the beta particle. What's the beta particle? What are beta rays? Do you have this in your curriculum? Do you have this phrase, alpha rays, beta rays, gamma rays? You have that in the curriculum? It's still there? In chemistry? Chemical kinetics? I wish there's a mass extinction of the people who use this terminology still, because it's 110 years old, 120 years old. There's nothing mysterious about beta rays. They're not. They are electrons. And we know what gamma rays are. They're very energetic photons. And we know what alpha quote-unquote rays are. They're helium-4 nuclei. We should just call them by their right names. Can you have helium-3? Can I have helium-3? Helium must have 2 protons. So 2 protons and a neutron. And turns out, remarkably enough, it's stable. It's perfectly stable as an isotope. What about helium-5? It's possible to have that too. These are, you can go on adding. Helium-6 becomes very unstable and so on. But you can go on adding neutrons. It becomes too neutron rich, it again decays in this fashion. If it becomes too proton rich, it also decays. So there's a little band of stability that sits there. Yeah.
What is the force which causes, or what is the reason which causes too much neutrons to immediately decay?
Because the force is not, the binding is not, it's too shallow a well in that sense. And there are quantum fluctuations of a particle inside this well. So there is no such thing. When you have, in quantum mechanics, if I put a particle inside a potential well of this kind, which is due to some other particle, say, in its vicinity, then this is the equilibrium point here, because at this stage, till here the force is repulsive. It's minus the derivative of this potential, which is negative. So you get a positive force outwards and it's unstable. It pushes it out. Out here it pushes it in, and that's the equilibrium point here. This is a classical picture. In this potential, if you put a particle, where is the equilibrium point? At this energy, there is no kinetic energy, the particle is at rest at the bottom of the well. But that violates the uncertainty principle, because it says you know its position and momentum immediately at the same time. That's not correct. There's always some 0 point energy, some fluctuations about it, and the ground state energy is somewhere here. And as you increase the excitation, it goes up further and further. Out here it becomes free completely. Because of this, pardon me, yeah, so because of this quantum effect that you have what's called 0 point motion, it's not at rest. You can't imagine it to be at rest or something like that. And these fluctuations can become strong enough for the particle to not have a bound state at all, to just move out. Depends on the potential once again. So the nuclear force is complicated to explain, but we understand a great deal about it. Yeah.
So is there any mathematical way by which we can determine the stability? Like for helium, we considered like, He5 is also
sure.
possible,
Yeah,
and so on. Is there any like formula?
Yeah, there is. There are several ways of testing stability. Yeah. Like you said, there are mathematical formalisms to test stability. Okay. It's not as simple a matter as this, because maybe this is time for me to explain little bit about the standard model. I've got some transparencies here, so let me show you. You see, if this well is too shallow and the particles got a very low mass, it executes higher and higher amplitude 0 point oscillations, as they call it, till there is no binding at all. It escapes out. It's not possible to have a stable bound state in this potential, purely for quantum effects, due to quantum. Classically, yes, the moment you have a well, however shallow it is, there is an equilibrium point. But quantum mechanically, that's not possible. To give you a physical example, if you take helium, for instance, it's a very weird substance. It looks like an inert gas to start with, very harmless, doesn't react chemically with anything else, and so on. But helium itself has got very, very exotic properties. If you start cooling down helium, it does not liquefy easily. It takes very low temperatures to liquefy. It's a gas with the lowest liquefaction point. Does anyone know at what Kelvin it liquefies? You need at about 4.2 Kelvin, that's right, but you also need 25 or 28 atmospheres pressure. So under heavy pressure, at 4.2 Kelvin, it liquefies. And then as you go lower down, it liquefies and becomes a superfluid. It's in a liquid form, it becomes a superfluid at 2.18 Kelvin. And then it moves without viscosity, it has all kinds of exotic properties, etc. As you go further down to millikelvin range, it becomes a solid, but it becomes what's called a quantum solid, because this binding between helium atoms is extremely low, and because of the 0 point motion, the amplitude of this motion becomes comparable to the distance between neighboring atoms. The moment you have that, solidifying something becomes magic, becomes nearly impossible. So when you solidify helium, it's more like a sponge, because in the lattice you have a lot of vacancies, and this helium jumps around from one point to another, etc., etc. So it's a very weird solid, cannot be understood classically, needs quantum physics to understand. Helium-3 also has similar properties. It's even more exotic than helium-4 and becomes the superfluid itself at millikelvin range, etc. And the list of properties doesn't stop there. When you hit the temperatures which are incredibly low, like microkelvin, 1 microkelvin and less, then helium exhibits magnetic properties. You can have an antiferromagnet, a magnetic antiferromagnet, etc. So there are lots of interesting things that happen at very, very, very low temperatures indeed. Okay. Coming back to what I wanted to say here was this. You start with characteristic energy scales in every range, and then as you go down, as you go from molecules to atoms to nuclei to subnuclear elementary particle physics, you have to have higher and higher energy probes in order to probe deeper and deeper into nature. The Large Hadron Collider probes fairly deep into nature. The characteristic length scales at that stage are of the order of 10 to the minus 18 meters or less. So that's a millifemtometer, if you like. I don't know what it's called, an atometer or something like that. Okay. So in that sense, the LHC is the world's most powerful microscope and the length scale of the order of 10 to the minus 18 meters. Okay. We have come to a sort of tentative understanding of the universe around us, matter around us, in something called the Standard Model. Let me say a little bit about what it is. Yeah. Before that, a little background. The cornerstones of our understanding of physics, fundamental physics at this level, are twofold. One is special relativity with energy mass equivalence implied, and the other is quantum physics, the wave particle duality implied. When you put these two together, you have a version of quantum mechanics which is called quantum field theory, which includes the study of fields and quanta. So every particle is regarded as having a field associated with it, and the particle itself is what is called the quantum of that field. When you quantize it and apply the rules of special relativity and quantum mechanics, you get the properties of the quanta of the field here. And these fields are governed by equations of motion determined by something called an action principle for all the fundamental interactions. Okay. So there's a formalism, a long-standing formalism, which is about 100 and something years old, which helps you understand this business in a clear way. What plays a fundamental role in our understanding the so-called symmetries, and I should write here what these symmetries are. There are invariance principles which lead to conservation laws, which implies an observer-independent description, and then there are selection principles, selection rules, guiding principles, classification schemes, and so on and so forth. So let me spend a couple of minutes talking about conservation laws. Conservation laws, like the law of conservation of momentum, the law of conservation of mass, the law of conservation of angular momentum, linear momentum, energy, and so on and so forth, arise because of properties of space-time. This is now our current understanding of where these symmetries come from. If you have a physical system whose description is independent of some variable, I'll give an example very shortly, then you have a conservation law behind it, potential conservation law. For instance, take this object on this table. I put this object on this table so that I've eliminated the z coordinate. It's on the table here. And it moves in the z on this table here. What is conserved? What momentum is conserved? So let's make this very precise. There is no force on this object on this table, other than the fact that it stays on this table. That's a constraining force on this table, but nothing else. It's imagine a ball bearing or something like that. It's free to move on this plane. Okay. There's no z momentum in the z direction because it's on this table and the height is fixed. You'll have angular momentum about some origin, specified origin conserved. Yes, there's no torque on it. There's linear momentum conserved and so on. Now, what is this property actually due to? There's no force on it. So the momentum is, but why should it be conserved at all? This is, of course, according to Newton's law of motion, but where does that come from? Where would you think? I'm going to give you an intuitive feel of where this law is coming from. Where does it come from? Why are the x and y components of the momentum of this object conserved? Well, would you agree if I said that they're conserved because on this space of this table, there is no distinguishing point at all. Every point is equivalent completely. There's complete translation invariance. It doesn't matter where the origin of coordinates is on this point, on this table, right? So when you have translation invariance of the energy of the system, for instance, then you would have a conservation law of this kind. When you have rotational invariance, which is also available on this table, you have angular momentum conservation. And when you have time translation invariance, then under the origin of time, if you shift it, nothing changes at all, the rules don't change, then you have the potential for energy conservation. The moment you apply a symmetry breaking effect, like a force on it, like I take it out and now there's gravity acting on it, then even though the x and y directions are completely equivalent, the momentum will still be conserved on those directions. The z component is not, and the particle will certainly see motion, change of momentum in the z direction. So if I throw this object, it moves in a parabolic path, but you agree that at every point, the x and y components of the momentum are not changed at all. Only the z component is changing in projectile motion. because there is a gravity field which breaks the invariance under translation. This point is not the same as this point, but this point is exactly the same as this point or this point here. Okay? So it implies that the moment you have symmetry under or invariance under some set of transformations, there is the potential for a conservation law. And that's the origin of all the conservation laws that we know. This fact, a very, very basic fact, was mathematically discovered first by possibly the greatest woman mathematician ever, a lady called Emmy Noether, and it goes under the name of Noether's theorem. Around 1912 or so, she made this discovery. And she worked at Göttingen. She was one of Hilbert's students, and she made this very, very fundamental discovery. So, Noether's theorem is very basic to fundamental physics, continues to remain so. And then you have selection rules. There are rules whose origin we don't really deeply understand. For example, the conservation of charge, the conservation of various quantum numbers like the lepton number, the baryon number, and so on. We understand them to quite some extent, but we don't really fully understand where these conservation laws come from, etc. But they're there experimentally. So that's why I've said that the symmetries can be space-time related, like the conservation of momentum, linear momentum, energy, etc., or internal, like charge, spin, etc., etc. And the symmetry could be manifest or open or covert or hidden, called spontaneously broken, and I explain what that means in a minute. So our current wisdom, called the standard model, says that matter comprises of two classes of objects called quarks and leptons. And there's a kind of deep symmetry between them, which again we don't fully understand here. And there are several types of quarks and leptons, but what is common to them is that they all have spin half. You're already familiar with the idea of spin of a particle, elementary particle. And all of them are therefore fermions, spin half fermions. But they come in many flavors, colors, and other quantum numbers. They have a whole variety of quantum numbers associated with them. The forces between these objects, these comprise standard matter, but the forces between these objects are governed by the exchange of quanta of so-called gauge fields. And you heard some of it from Professor Libera. There is the photon, there is the W plus minus and Z naught, all of which have spin 1, and they govern the electroweak interactions. And then we believe the gravitational force, if quantized, is a spin 2 quantum. It's called the graviton. Nobody has seen a single graviton so far. We've seen single photons. There are experiments which detect single photons. Can you think of why we have not seen a single graviton? Might not, you can't see it. I mean, when I say see, I mean without instruments. I don't. Why do you think we've not had? No, the size of the graviton, they're all zeros. There's too much. Well, yeah, intuitively you're on the right track. Yeah. The interaction itself is so weak. Capital G, Newton's gravitational constant, is so small in real terms that it takes a large number of particles before you see a discernible effect. This merger of two black holes that we saw from 1.3 billion years away, etc., it took a long time to come here. That was a massive event. It generated a huge, enormous amount of energy in gravitational waves. But the gravitational waves are so weak, in a sense, that by the time it came here, you needed incredible detection equipment to even see it. Very weak force. And that factor of 10 to the 38. So to produce an effect comparable to what one photon produces, you need 10 to the 38 gravitons, very roughly speaking. And that's why it's impossible, probably impossible forever, to see single graviton experiments. Okay? This might be famous last words. There might be a clever trick for seeing them. We don't know. I don't know of any yet.
The standard model suggests these particles exist when they consider these as forces, gravitation as a force.
Yeah.
If it might not be a force, as Einstein suggested, then we might not find graviton.
Might not be a force in what sense?
In the sense that a standard model suggests it as.
Yeah, the graviton is not included in the standard model. We think that gravity is mediated by a spin 2 object called the graviton. But as I said, we have not seen single gravitons. We can't think of any single graviton experiments and so on. So there is a group of people which thinks that gravitation doesn't come under this umbrella at all. It's not a fundamental force at all. It is what's called an emergent phenomenon. It has thermodynamic connotations and so on. We're not going to get into that here. Yeah, every time I fall down, I observe gravitons, a large number of them. If this force is mediated by gravitons, you certainly have. By the way, I should also give you some insight as to why the nuclear force and the weak force, electroweak force, took much longer to discover than the gravitational force and the electromagnetic force. Electromagnetism, understanding the nature of this force is one thing, but detecting them by human beings is another thing. Human beings detected electromagnetic waves when they opened their eyes and looked at the world around them. Certainly did that, right? Similarly, gravitational force and so on. Why do you think it's the case that this is happening? Why were these forces known to mankind much earlier than modern times when you discovered two other forces? They had a longer range. What's the range of the inverse square law? Where does the Earth's gravity stop? And don't say in a satellite. It's not true. In principle, where does the Earth's gravity stop? In principle. In practice, it gets extinct. In principle, infinity. Right? 1 over r squared. There's no length scale in the problem. It goes on all the way to infinity. It's what's called a long-range force. They are macroscopically observable. You can observe it in macroscopic effects and so on in the daily world without going to atomic and nuclear levels and so on. That's not true for the weak force, because of the weak force mediators, the W plus minus and the Z naught have mass. The moment the exchanging particle has got mass, the particle exchange has mass, the range becomes finite and exceedingly short in these cases. So the nuclear force and the electroweak force have ranges certainly smaller than 1 Fermi, definitely, and even smaller. But the electromagnetic and gravitational forces have a lot of. There's another reason why you would not see, it was believed for a long time that the neutrino, it was believed for a long time, when they thought there was only one kind of neutrino, was a massless particle, zero rest mass, but a fermion, spin half, but zero rest mass. We know today that the neutrino comes in 3 flavors. There's a electron neutrino, there's a tau neutrino, and there's a muon neutrino. But we know that at least one of them must have mass. Okay. It's possible the electron neutrino still is massless because we can only put lower bounds on it. We can't say something is exactly equal to 0. But if you assume that it's massless, why have we not seen a force due to the exchange of neutrinos? If it was massless, then the force should be infinite range. So there are 2 effects here. To see a force, it must be macroscopic, number 1. It must extend over macroscopic lengths. But you also need to have a large number of quanta, like the gravitational field or the photons or something like that. Why is it not possible to have a large number of quanta in the same state for neutrinos? Neutrinos are fermions, spin half. They accompany the leptons, the usual leptons. Each kind of lepton, whether it's the electron or the muon or the tau lepton, they have their own flavor of neutrinos associated with it. They are fermions. And at least one of these 3 must have masses. That we know from other experiments and so on. The lightest one may be massless. The electron neutrino may be massless. Suppose it is, then you should be able to observe a macroscopic force due to the exchange of neutrinos. There are 10 to the 17 neutrinos passing through each one of us, each square centimeter of each one of us every second. The interaction is so weak that neutrinos can pass through a lead sheet half a galaxy thick and not have an interaction. But we know how to detect them. We've got detectors for them because you just put a lot of detection, a lot of them together. So why would you say that, what would be your guess? Why have we not seen a long-range force due to neutrinos? What did I say was the spin of a neutrino? Which means what sort of statistics would it obey? The Fermi-Dirac statistics. And what is the speciality of Fermi-Dirac statistics? Have you heard of the Pauli exclusion principle? You cannot have too many of these, more than one of these particles in a given state at a given time. To detect it macroscopically, you need to have a large number of quanta in the same state. And you can't have more than one. And that's simply too weak. Okay? So there are many subtle effects at play here, and we understand some of these things, and many of them we don't understand. And now I come to an idea called spontaneous breakdown of symmetry, on which this entire gauge theory business for the last 60 years is based. Okay. And I'll try to explain it in terms of a simple analogy, very simple analogy. It's only an analogy, but imagine that you had a potential which looks, a well which looks like that. This is a potential well. It's like the bottom of a wine bottle. The bottom, there's a rim, and then there's a little maximum in the middle of the bottle at the floor. If you put a particle in here and balanced it on top of this maximum, local maximum of the potential, it's in equilibrium. But is it stable or unstable? It's unstable because you push it in any direction, the slightest fluctuation, it's gone to the ground state, goes down here. It can fall and stay at any one of these points in the rim here. They are all possible ground states. They have exactly the same energy, in this case, zero potential energy at the bottom. Okay. Is there a unique ground state, or is there a whole continuum of ground states? It could have fallen here or here or here, anywhere on that rim. They're all completely equivalent points. But the moment it falls into any one of them and it remains there, that ground state is not rotationally invariant, because if I now rotate the bottle, it moves to some other point. Here. So you have a very weird situation here. It looks very ordinary, but you have a very deep point here. You have a weird situation in which the ground state of this object does not have the same symmetry as the potential itself has. The potential itself is circularly symmetric. If I rotate the bottle, nothing changes. The shape looks exactly the same. But the ground state in that potential does not have the symmetry of the potential. Whereas in normal circumstances, when you have the ground state of a system, it will have the symmetry of whatever the energy surface is for that system. So pushing it to any one point here breaks symmetry, and if nature has already done it for you due to quantum fluctuations, you have what's called spontaneously broken symmetry. This is exactly the symmetry that is broken when you have a ferromagnet from a paramagnet. If I take a piece of iron and keep it outside, above its Curie temperature, in what direction is there a magnetization? Is there a magnetization at all in the absence of a magnetic field? I heat a magnet above its Curie point, the magnetization is gone, because the magnetic moments are all pointing in random directions and therefore have zero net magnetization. But if I go below the Curie temperature, then the magnetization is in some specific direction. How does it choose the direction? Completely at random. If I put a small magnetic field and align all these moments and then cool down and switch off the magnetic field, I have a permanent magnet. That's how you make a permanent magnet. But this magnet has spontaneously broken the symmetry of the Hamiltonian or energy of the system, because that says that there should be zero magnetization completely. Right? So you have what's called spontaneous breakdown of symmetry, and that leads to this phenomenon of the ground state having a symmetry less than that of the system in Hamiltonian itself. This means if I take this ball bearing which is sitting on the rim, do I need any energy to move it around this rim if there is no friction at all? They're all at the ground state, the same potential energy, and I can move from one point to another. I can push it around. There's no friction with no energy. Those are called what are called Goldstone bosons. This was known in the 1960s. But what took place after that was interesting. These people, Higgs among all of them, to start with, Englert and Braut, and then Hagen, Guralnik and Kibble, asked the question, what happens if you have these gauge particles exchanged for these fundamental forces and also have spontaneous breakdown of symmetry at the same time? That is the famous Higgs mechanism, for which Higgs got the Nobel Prize, and that led to the modern electroweak theory and color theory and so on. The analogy I gave here was the following. Once you put the ball bearing in one point here in the minimum, in this rim, you have broken the circular symmetry of the system, because this state is not the same if you move it to some other point. It goes to, pardon me? If I rotate the bottle about its midpoint, about its axis, does the potential change the shape? But does the coordinate of the point where the ball bearing has come to rest change or not? Changes. That's all I meant. So it goes to a new state or a new point. They are the same in energy, but there's an infinite number of such possible points. And you can go from, and once the system is frozen at one point, it's broken that symmetry. I label the states of a particle as its coordinate on this rim. Right? And it can be anywhere on that rim from 0 to 2 pi. They're all different quantum states. They have the same energy. But the system has accidentally got frozen at one particular value of this angle. I don't need any energy to excite it. Yes. So I would therefore expect quantum fluctuations to move it from one point to another. And that's exactly what the Goldstone bosons are. That's exactly what happens. If I didn't have any quantum fluctuations and I had an absolute vacuum with nothing in it, then this would not happen. But the moment I have quantum fields fluctuating, this can happen. Yeah, a general definition of spontaneously broken symmetry is the following. It has to be taken with a little bit of caveats and so on. If you have a system whose energy, the technical word is Hamiltonian for the energy. I don't expect you've heard that word. Somebody talked to you about Hamiltonians? Who? She talked about Hamiltonians? Okay. They are operators whose eigenvalues are the energy of a system and so on. So let me just call it energy. So if you have systems whose energy function is unchanged under some transformations, whatever be the transformations, but the ground state is not unchanged, then you have what's called spontaneous breakdown of symmetry. In very simple terms, that's what it is. Now I have to give you, this is one particular example of it. Now I have to give you the caveats. It happens only due to quantum mechanics. It happens only if you have an infinite number of degrees of freedom and so on and so forth. Okay, so those are the extra pieces of information that I need to put down. Otherwise, quantum fluctuations will restore symmetry. So I gave this only as an analogy. If you really took a bottle like this, and put a particle here, it would remain there if it's classical. But if you put a quantum mechanical particle, then by the fluctuations, by quantum fluctuations, it will actually spread out around this entire ring. But if you put a quantum field there, which has an infinite number of degrees of freedom, then it will not. So a little bit of history here. Of these people, the only people who are alive to receive the Nobel Prize was Higgs and Englert. Brown passed away before he could be given the Nobel Prize many, many years ago. Guralnik is no more either. And then the prize can only be given to 3 people at a maximum. So it's historical, various historical effects took place and so on. Higgs, in fact, gave the simplest version of this mechanism of his, named after him. Englert and Brout and this group here gave a more general version, the non-abelian group version of it, which is what is used, by the way. So it's a sort of a little bit ironic that somebody asked me.
Yeah. Do we know of any of the causes, like what are the factors on which these fluctuations depend upon the quantum fluctuations?
Yeah, we know a lot about them.
Could you mention a few factors that it depends on?
Where do they come? You want to know a very deep question. Why do they occur? First of all, what are fluctuations? Let me ask you. If you take an object and you take a physical quantity and take its average value, that's the first moment, or mean value. About this mean value, if there are sources of uncertainty, there are fluctuations which are measured by the variance or the standard deviation. In nature, there are two major sources of intrinsic fluctuations. One of them has to do with contact of a system with the environment. Then the temperature causes the fluctuations. The fact that you have thermal fluctuations. The other deeper version cause for fluctuations is the non-zero value of Planck's constant. So in a nutshell, if you put Planck's constant equal to 0, all the quantum effects go away. It's small but non-zero, which makes the universe what it is. Okay. And fluctuations are important. Otherwise, like I showed you, the molecules of air, they would all be condensed at the bottom of the floor and we'd all be dead. So its fluctuations are all important. Okay. Let me skip this and come to the interesting part. For those who are interested in where the Higgs field, somebody asked me where the Higgs field was and what it did, how did it give mass and so on. I have written this little line of equation for the Lagrangian density in the standard model. If I wrote it out in the full notation, it will take about a page or so, but I have not done that for obvious reasons. There are a whole lot of symbols here. So right now this is just hieroglyphics. But the so-called phi is the Higgs field, and notice that it couples to the matter field here. So this is the term that's leading to the mass of the particles here. Professor mentioned that the Higgs field gives mass and so on. It gives mass in this model way of looking at it by this coupling term here. And by the way, this Hc stands for Hermitian conjugate, which makes the whole thing real in some sense. So let me not get into this. But let me recall to you that the basic quantity is the energy-momentum relationship, the basic point, where you have the energy and momentum related by this quadratic relationship. And I already mentioned this, what's relativistic and what's ultra-relativistic and so on. This little table I have here will give you some idea of what relativistic physics is all about. It's a very simple thing. So let's take various objects and look at the rest energies, and then the kinetic energies which you give them under various circumstances, and take the ratio of the kinetic energy to the rest energy. If you look at the Earth in orbit, the rest energy of the Earth's mass, mc squared, if you take the mass, is 10 to the 41 joules. It's quite a very large amount of rest energy here. It's moving around the sun in an orbit, and you can calculate the kinetic energy in this orbit. It's actually essentially non-relativistic because its kinetic energy is only 10 to the 32 joules, which is 10 to the minus 9, the factor 10 to the 41 here. So the ratio is 10 to the minus 9, much, much less than 1. Therefore, the Earth can be regarded as a non-relativistic object when it moves around the sun. It's extremely small compared to its rest energy. If you look at Mr. Usain Bolt, who I understand has retired, he was doing the 100 meters in 10 seconds or less. His rest energy is 10 to the 19 joules, assuming a mass of some 60 kilos or something like that, 70 kilos. His kinetic energy is 10 to the 3 joules, and the ratio is 10 to the minus 16. So he may be the fastest man alive, but he is essentially very, very non-relativistic. Don't have to apply relativistic corrections to his motion at all. If you look at an air molecule at room temperature, the system is not much better. We treat in thermodynamics everything non-relativistically, and you wonder why, because these are particles that are very small, moving very fast. Well, at room temperature, the rest energy for the molecule is typically 10 to the minus 9 joules for a single particle, but the kinetic energy is 10 to the minus 20 joules. So the ratio is 10 to the minus 11, which is incredibly non-relativistic, more so than the Earth in orbit. Now look at what happens if you take a TeV proton, tera-electron volt proton, in the Large Hadron Collider. It's 1 GeV. A proton or a neutron has a mass of 1 GeV in energy units, or 1 GeV multiplied by c squared, divided by c squared in mass units. So 10 to the minus 10 in joules, 10 to the minus 7 is 1 TeV. So the ratio is 10 to the plus 3. In other words, the kinetic energy is 1,000 times the rest energy of this object. It's incredibly non-relativistic, ultra-relativistic. It's moving at 99.9999 whatever percent, 5 decimal places the speed of light in vacuum. And when you have that, anything can happen. It's like the analogy I frequently give. If you take 2 bricks and slam them against each other, you get brick powder. But you take 2 TeV protons and slam them against each other, you get jets of thousands of particles, many of which are heavier than the proton, because the energy is getting converted to mass. Literally. So particle plus particle leads to jets of hundreds of particles, subject to conservation laws like conservation of charge and momentum and energy and so on. But the energy of this object is getting converted to pure mass, particles and antiparticles. So it's like you slam two bricks together and you get two houses coming out, house and anti-house. It's much worse than that. It's actually much worse than that. Okay. The moment you have that situation possible, the question of whether the houses were inside the brick to start with and so on becomes a meaningless question. So you shoot protons at each other, two protons, and out come thousands of particles. The question of whether these thousands of particles existed or were inside the proton, quote unquote, is a meaningless one. It's the energy that has been converted to mass.
A particle and an antiparticle collide together or interact with each other. The energy should be in which form, or energy can be in any form?
What do you mean the energy should be in form? In this case, in the collider physics, it's always in the kinetic energy form.
Like have an electron and an anti-electron,
Yeah.
and they collide with each other. What form of energy will come?
What do you think it is? It's kinetic energy.
No, not that. Matter and antimatter interact with it.
Yeah.
What energy do we get?
What do you mean? What are the types of energy that you know of?
Like
Pardon me?
electromagnetic wave, photon.
There's electromagnetic energy definitely involved. There's electromagnetic fields. They interact via electromagnetic fields and strong nuclear forces. At this stage, in the proton-proton collision, you're asking, is the energy or is the interaction electromagnetic? Not entirely. It's mostly strong interaction, nuclear interaction.
When a particle and an antiparticle interact, we get energy.
Yeah. Oh, in what form? That energy comes out?
Yes.
Gamma rays. Mostly gamma rays. But the particles that come out also carry energy. Rest energy plus kinetic energy of their own. Yeah. So words like mechanical energy, thermal energy and so on are in the macroscopic world, not in the submicroscope. Yeah.
Yes, sir. I still have a doubt regarding the standard model.
Mm-hmm. Just
how?
one?
Huh? No. As of now, it's just one question.
Amazing.
As of now, from my understanding, it's just one question for now. There are a lot of other questions which I don't even understand. Okay. So, we said that we got these bosons from the field of that particular fundamental force. How did we convert the field into a particle?
That's a good question. What's the connection between fields and their quanta? That requires a procedure for quantization, something called quantization. In fact, something called second quantization, which is a rigorous procedure by which you start with classical fields and then you impose the laws of relativity and quantum mechanics on it, and you get the quantum field. And the quanta of these fields are manifestations of energy and momentum in lumps, if you like. So the quanta emerge in a natural way in this procedure of quantization. That's not an answer to your question, but these are interchangeable. Just like wave-particle duality, the waves and the particles are just two facets of the same reality. In exactly the same way, the fields and quanta are two facets of the same reality.
Sir, so but this process doesn't work for gravity. It doesn't work for gravity when it comes to like reconciling it with general relativity.
This process does not work for gravity. Yeah. Because what happens if you apply these rules is that you get a lot of infinities. Physical quantities which should be finite become infinite. If you ask, I give you a point mass, what is its gravitational self-energy? It becomes infinite. The calculations show infinity as the answer. That same thing happened in electromagnetism, but it was solved by a procedure called renormalization, which was finalized around the 1940s and 50s, and since then people have refined it, and it works extremely well. Ditto for the electroweak interaction. The renormalizability of electroweak interactions was established in the early 1970s. But in spite of decades of very hard work by a large number of people, they have not been able to quantize gravity consistently, because it's a very non-linear theory, necessarily non-linear, couples to itself extremely strongly. So we don't know. This is what string theory was attempting to do. It was attempting to go beyond quantum field theory and evolve a procedure by which the infinities of quantum field theory were all removed and you got finite answers. And what we've discovered is that to have a consistent field theory, string theory, you need to work in higher space-time dimensions, 10 or 11 or whatever it is. But the unfortunate thing is, in spite of decades of work, we've not been able to get a low energy limit of string theory which corresponds to the actual physical particles we see around us. So there's no experimental test. It's not unique. In fact, the problem with string theory is not that it's wrong, but that it's not predictive. It turns out a very large number of possible particle spectra are consistent with string theory. So it doesn't lead to a unique low energy limit, which was the hope at that time. But that hope is not come true.
Sir, what exactly is the difference between energy and mass?
Nothing. Nothing. That's the moral of the story. That's what Einstein taught us. There's no difference. Its total energy is increased, and that's all. That's because you've not done enough. If you do sufficient violence to that mass, then it will show up as energy. That's what it's telling you. You have to pull it apart or hit it with an anti-ball. So the energy in normal particles is locked up, but you can release it in these collisions. It makes perfect sense according to relativity. You have to overcome your normal biases, which you call intuition. They don't operate in this subatomic world. You don't really understand inertia, right? Just a property, a name you're giving for certain kinds of behavior. You don't really understand it at that level. Yeah, the moment you have macroscopic objects.
Yeah. How do we define when energy is locked
Heat
up
is
in
an
mass?
average value, right? Heat is an average kinetic energy of a molecule multiplied by the number of molecules is the heat energy in a system.
So my question is, how do we define when energy is locked up in a mass? How do we define that? Like, for example, in this water bottle, like the particles and all that, the energy is locked up as that particle. So how do we define, like, what does it mean to be that?
Like anything else, when you want to find out what it contains, you smash it. Take it apart.
But why does energy want to go and be this mass?
There's no question of why. That's how nature operates. We can't now dictate to nature why would you like to do this or like to do that.
When you do try to take it apart and try to observe it, won't it change its quantum state?
Pardon me, say that.
When you do try to take it apart and try to observe it, it will change its quantum state at some point. So
The cleverness lies in taking it, smashing it so that it doesn't fall apart. You can see what you want to see, etc. If I were to try to take a piece of iron apart, I need something called a cohesive energy to remove the bonds. What do you think is that's the order of? We talked about atoms, nuclei, subnuclear, etc., etc. In the other direction, in condensed matter physics, what is the typical cohesive energy? How much energy does it take to take out one atom from a piece of iron? That's called the cohesive energy. It will be of the order of 10, 15, 20, whatever it is, electron volts from a crystal. You don't need mega electron volts to do this. You want to smash into the iron atom and then look at it, then you need much higher energies. You want to smash into its nucleus, then you need even higher energies. So that's, you have to test and repeatedly test and hypothesize and observe. There's no such thing as a wrong result. I once asked a student who was doing some magnetism experiment why he took the 4 readings and stopped at 4. And he said, because he got the right answer the 4th time. That's not the purpose of an experiment. Think of the person who did it the first time. He didn't have an answer ahead of him at all. So you have to try. You have to hypothesize. You have to see if the predictions are, test the predictions repeatedly. Why can't I go on increasing the energy of the Large Hadron Collider? What happens? I need bigger and bigger. Right now it's some 26 kilometers in circumference, this circular accelerator, there are proton rings, intersecting proton rings. And it takes, if I have a bigger circumference, then I have to make the whole thing a vacuum and so on. Then I have a bigger accelerator, I can go to higher energy. Can I keep doing that? Eventually, it turns out that to really do experiments that cosmic rays provide us, they provide us with particles which are like 10 to the 7 tera electron volts, etc. You will need an accelerator whose circle is as big as the galaxy itself, which is a little not feasible. I would say it's not very feasible to build an accelerator that size. But can that go on in principle? Can I go on increasing it? Do you think that it will work? I want to go to smaller and smaller distances and see whether really physics still operates at the smallest distances. It will get much larger, etc. But what happens is when you pack an energy called the Planck mass, the equivalent of the Planck energy, it's of the order of 10 to the minus 5 grams. It's a large amount of energy for a single particle. If you pack that amount of energy in a space-time volume whose linear dimension is something called the Planck length, formed out of G, C, and H cross, the system just becomes a black hole and disappears. So the accelerators cannot go on forever. Already we are reaching the limits of possibilities. You could possibly think of an accelerator whose circumference is that of the Earth's orbit or something like that. Could think of it that way. But even if you had one as big as the galaxy, it's not going to help. Because eventually the system is just going to become a black hole and disappear. So there's a finite limit to this business.
Sir, in the LHC, when the energy released by the collision gets converted into particles, do we know what happens then? Like how that transition happens?
Yeah, we know what's happened.
Yes,
We test our models. We test the standard model. That's been tested over and over again.
So what happens as the energy is being converted into mass? How does it get converted into mass?
You cannot speak of the precise instant of the interaction because of the uncertainty principle. It's not an instantaneous interaction. The more precise you make that time interval, the more imprecise the energy becomes. And you can't beat the uncertainty principle.